We're going to mix 5.2 and 5.3 together so that we can learn how to write polynomials in factored form. Then we can go in reverse to write them from their zeros, and then we can also go ahead and solve the polynomials. First off, writing them in factored form and then solving. We'll factor polynomials with a lot of the same methods we used for factoring quadratics. We first need to make sure that it is in standard form, so we're going to add that 4x cubed to the other side. And standard form is going by decreasing exponents. So it becomes x to the fourth plus 4x cubed now, since we're adding it over, minus 12x squared, all equals 0. And we can use our factoring flowchart to know where to start. Starting at the top, we always look first. Do we have a greatest common factor? Looking at your problem, they both have an x squared in common. That's where we're going to start. We'll pull out that greatest common factor of x squared. That leaves us with x squared plus 4x minus 12 on the inside is all equal to 0. Now that we've factored out that greatest common factor, we're left to look at how many terms we have. We had 3 terms since it's a trinomial, and we cannot take the square root of the first or the last term, so we know for sure it's not a perfect square trinomial, which tells us we will use the AC method. I'm going to take those numbers that multiply to negative 12, but add to a positive 4 to replace that middle term. So that would be x squared plus 6x minus 2x minus 12 would work. Split it in half. Pull out the greatest common factor again. So we'll take out an x, leaving you with x plus 6. On the other side, pull out a negative 2, leaving you with x plus 6 on the inside again. Now we can bring it all together. We'll have the common set of parentheses, the x plus 6, the leftovers with that x minus 2, and then we can't forget this x squared that we pulled out from the very beginning. Remember to bring that back down, and we have the x squared on the outside. So this is our factored form. X squared times x plus 6 times x minus 2. All those values that multiply together to get us back to the original equation we started with. But when we want to go further and find those zeros or solve for x, we need to set each part that has an x equal to 0. So we can take this x squared and say x squared is equal to 0. Well, take the square root of both sides. Square root of 0 is still 0, so there is our first solution. Also take x plus 6, set that equal to 0, so x is equal to a negative 6. And then take the x minus 2 as well, and set it equal to 0, so x is equal to positive 2. And this gives us our 3 solutions. X is equal to 0, negative 6, and positive 2. Going back to look at the methods we used, we started off by using the greatest common factor. Then we ended up using the AC method to factor out the rest. On this next example, we again start by putting it in standard form. So we'll have 64x cubed, subtract 27 to the other side, and that will all equal 0. Now we're ready to consult our flowchart. First thing, we're looking for that greatest common factor. There is no number they have in common, so there is not one. We're going to skip that step. Next, looking at how many terms, we have a binomial, so we have 2 terms. Now we have a couple different options. First, do we have the difference of squares? So again, we had 64x cubed and 27. Well, 64 is a perfect square, but x cubed, we cannot take the square root perfectly. Same thing with 27, so we're going to say no. Then we have 2 options. Is it the sum of squares? Well, again, we said there is no squares, so it's not that option. We can look. It must be now the sum or difference of cubes. Notice here that we have some value to the 3rd power. We can rewrite this expression using these formulas. But since we have subtraction between our first and second term, we're going to be using the difference of cubes. Here is that difference of cubes formula written out. It's kind of like when we were doing difference of squares, where we want to rewrite the original expression as some number, but this time it's going to be to the 3rd power. If we're looking for one number multiplied 3 times to get us to 64, that would be 4. Then x times x would get us to x cubed, so we can say 64x cubed is the same thing as 4x all cubed. Then to get to 27, well, that's 3 times 3 is 9, 9 times 3 is 27, So 3 cubed is the same thing as 27. Now we know that our a value is 4x, and that b value is going to be a positive 3. And we can plug it into the difference of cubes formula. So we'll have 4x minus 3. Then notice how here it is a squared. Well, if a is 4x, we need to multiply it by itself to square it, so that will become 16x squared. So 4x times 3 will give us positive 12x. Lastly, we end up with adding b squared, so 3 squared is 9. And this is our factored form. 4x minus 3 times 16x squared plus 12x plus 9. We would always want to check to see if we could go further, but the trinomial we make right here is not factorable. Therefore, we cannot factor anymore. But when we go to find the solutions, we can use the quadratic formula. So now we are ready to solve. We can take that first set of parentheses and set it equal to 0. We'll add 3, then divide by 4, so x becomes 3/4. Then, with this trinomial here in the middle, we're going to use the quadratic formula. And we'll want to use this method to solve because, again, it is not factorable. So this will give us negative b, or negative 12, plus or minus the square root of 12 squared, minus 4 times 16 times 9, all over 2 times 16. Working underneath that square root, we're going to have 144 minus 576, which becomes negative 432. We can rewrite as negative 12 plus or minus. Remember, we still have that square root of negative 432, all divided by 32. We can break down 432, and I know it seems like a big number, but let's think about it. What are some numbers that fit into 32? Well, 16 is a big one. So what if we divide by 16? Well, 16 times 27 gives us 32. Break this down, we have 4 times 4, and we have already identified one pair we can take out of the square root. Break down 27, that's 9 times 3. Break down the 9 into 3 times 3, and there's a second pair we have to take out. So now we have negative 12 plus or minus. Multiply that 3 and 4 together, we're taking out, so that will give us 12. Remember, we have a negative, so we need to make sure we have an I now, and we have the square root of positive 3 since that 3 is left over on the inside. All of this divided by 32. Last thing is to simplify. We can divide all of it by 4. So now we have the solution of negative 3 plus or minus 3i square roots of 3 all over 8. But we also had that solution from earlier, and we also said that x is equal to a positive 3/4. So this is giving us our 3 solutions. 2 are imaginary, and 1 is real. Now to go back and look at what methods we used, there was no greatest common factor. All we used was the difference of cubes. This next example is already in standard form, so we can consult our flowchart of where to start. Alright, first thing, greatest common factor. We do not have a number or variable they have in common, so we're going to move on to the number of terms. We have 2 terms with this binomial, so first thing we're going to look for is, do we have the difference of squares? Well, we do have subtraction, so that's a good sign. Then we could take the square root of a 4th power, and we can take the square root of 16, so we are going to have the difference of squares. And this is the same formula that we used in the previous chapter. Similar to using the difference of cubes, we want to rewrite this as some value squared. If we want to get to x to the 4th, well, we'd have to have x squared all squared. If we wanted to get back to a 16, then we'd have to have 4 squared. So now we know that our a is x squared, our b is 4, and we can plug it into the difference of squares formula. So we have x squared plus 4 times x squared minus 4. Now, we might be tempted to stop here, but we always want to check to see if we could factor again. Here's what we just found. We're going to look at each set of parentheses to see if we can factor more. In the first set, we're looking for greatest common factor. We don't have one. Then we're looking at how many terms. Well, we have 2 of them. So again, we're going to look to see if we have the difference of squares. We have addition in this first set, so we cannot have the difference of squares. So we can move down. We don't have anything cubed. The only other option is the sum of squares, and our sum of squares is not factorable. So we're going to keep that pair as it is. Now we can take a look at this second factor. Again, looking for greatest common factor, which there is not one. It also has 2 terms, so we're going to look at the difference of squares. It is subtraction, and x squared and 4 are both perfect squares, so that means we can apply the difference of squares again, specifically to that set of parentheses. So if we rewrite the second set of parentheses as some value squared, that would be x squared, and then 2 squared would get us back to 4. So this becomes x plus 2 times x minus 2. Then we can bring down what we had from the previous step, which was x squared plus 4, and this gives us our completely factored form. X squared plus 4 times x plus 2 times x minus 2. Now we are ready to solve. We have that x squared plus 4 equals 0, subtract the 4 to the other side, so x squared is equal to negative 4. We take the square root, and x is going to be equal to both plus and minus. Remember, square roots always produce 2 solutions. Since it's negative, we're going to have an imaginary solution, and it will be 2i. Then we had x plus 2 equals 0, so x is negative 2, and x minus 2 also equals 0, so x is equal to positive 2. So now we have 4 solutions. We have x is equal to negative 2, positive 2, positive 2i, and negative 2i as well. Going back to look at our methods, here we use the difference of squares, but this time we actually used it 2 times. So always be looking for when you can use one method more than once, or when you can apply a second factoring method. With this last example, same thing. We need to make sure that it's going into standard form first. So we have negative x to the 4th plus 3x squared. Now it's going to be plus 54 is equal to 0. And we will start with looking for that greatest common factor. We might not have a variable or a number greater than 1 that they all have in common, but we do want to get rid of this negative out here in front. Because of that, we're going to divide everything by a negative 1. That will leave us with x to the 4th minus 3x squared minus 54 is all equal to 0. And make sure to put that negative 1 on the outside. We've already pulled out our greatest common factor, leaving this negative here on the outside. Then we have 3 terms, so we're looking for our trinomials. We do not have perfect squares, so we're going to move over to our AC method. So even though we have x to the 4th power and not x squared like we normally do, we can still find 2x squared values that are going to work. Let's see how this plays out. Looking for values that multiply to negative 54, but add to a negative 3, we could use negative 9 and a positive 6. But we want this to be a negative 3x squared, so we have to put the x squared on both of these terms. Previously, we had an x as the middle term, so we put x's on them. But since our new middle term is x squared, they need to be x squareds. Then we have the rest of our problem. And this looks like what we've done previously with factoring. We split it in half and factor by grouping. Pull out the x squared on the left-hand side, which leaves us with x squared minus 9. Pull out a 6 on the right, leaving us also with x squared minus 9. Put those common parentheses together, x squared minus 9. Take the leftovers, x squared plus 6. And also bring back that negative from the very first step. Now, we want to check again to see if we could go further. Whenever there are two terms separated by subtraction, we should always check to see if we can use the difference of squares. Since both x squared and 9 are perfect squares, we can apply the perfect squares formula, which tells us the square root of the first plus the square root of the second times the square root of the first minus the square root of the second. Rewrite out everything else, so x squared plus 6, and that negative on the outside. And here is our completely factored form. So negative times x plus 3 times x minus 3 times x squared plus 6. Now to solve. We're going to take everything, set it equal to 0. So x plus 3 equals 0. X minus 3 equals 0. X equals negative 3, and x equals positive 3. But we also have x squared plus 6 equals 0, so x squared equals negative 6. Take the square root of both sides, and x will be equal to I square roots of 6. And we have to remember that plus or minus since we get two solutions with square roots. So now x will be equal to negative 3, positive 3, I square roots of 6, and negative I square roots of 6. 4 solutions, 2 are real, 2 are imaginary. So the methods that we used here was first, we had a greatest common factor. Then we used that AC method, and we ended off by using the difference of squares, but only one time in this case. So we can see factoring has lots of different avenues, and it's our job to explore each avenue every time to make sure we are getting in completely factored form. Now, what was to happen if we worked backwards? What if we want to write a polynomial function from its zeros? We have what are called linear factors, and that's what we've been doing. We've been trying to break the polynomial down into sets of linear values that multiply back together. In linear factors, we always have x minus some number. But what that number represents is a 0, which we also know as an x-intercept, and we also call that a solution of a polynomial function. So if we want to know what the polynomial function is in standard form that has the zeros negative 2, 2, and 3, we need to substitute these in place of this number inside a set of linear factors. So we would have x minus, then we're going to plug in a negative 2. That's our first linear factor. Then we would have x minus a positive 2 is our second one, and x minus a positive 3 for our third. We can simplify, so this becomes x plus 2 times x minus 2 times x minus 3. So notice how the sign of the original number changes when we put it into the linear factor, because we're undoing the solving by putting it back in. Now it's just a matter of multiplying all of these binomials together. You can use FOILing or you can use the box method. Let's start off by multiplying the first two binomials together. We're going to have an x by 2 box and an x by negative 2 box, leaving us with x squared and a 2x, a negative 2x, and a negative 4. These middle terms cancel each other out, so now we'll have x squared minus 4. But we still had that x minus 3, so now it's a matter of multiplying these two together. We'll have x and negative 3. Multiply that by x squared and negative 4. This will produce x cubed minus 3x squared minus 4x plus 12. Take each term out in order. We're going to start with x cubed, then minus 3x squared, minus 4x, and plus 12. So here is the standard for polynomial that those 3 zeros or 3 solutions came from. Now, what if we're talking about imaginary roots? We hit on this in the last chapter. Imaginary roots always come in conjugate pairs, meaning if we have a positive imaginary number, we also have to have the opposite or the negative imaginary of the same number. So if one root is a negative 4i, then there must be another root and it has to be a positive 4i. So what is the cubic polynomial equation y equals some polynomial, px, in standard form with the roots 4 and 2i? Now they're only giving us 2 of the zeros, but because we know that there has to be a conjugate to the 2i, there also has to be a negative 2i as well. Here are our 3 zeros we're going to plug in. If we put each of these into linear factors, we would have x plus 4 now. Remember, we have to switch that sign. Then we'd have x minus 2i and an x plus 2i. And again, it's a matter of multiplying these out. This time we're going to use the FOILing method and we're going to multiply our imaginary conjugates together. So we have x times x gives us x squared. X times 2i gives us positive 2ix. Negative 2i times x is negative 2ix. And negative 2i times positive 2i is going to be negative 4i squared. Simplifying our like terms, we cancel out here in the middle. We know that I squared really becomes a negative 1. So this is now x squared plus 4. And we can bring down our x plus 4 from the beginning, and we're ready to multiply one more time. So we have x times x squared gives us x cubed. X times 4 is positive 4x. 4 times x squared is positive 4x squared, and 4 times 4 is 16. But now we need to make sure we put it in standard form, so decreasing exponent order. So we have x cubed plus 4x squared plus 4x plus 16, and there is our polynomial with those 2 imaginary solutions and 1 real solution.